So the idea is that Vincenzo Nicosia and Federico Battiston from the School of Mathematical Science in Queen Mary University of London, they are both working on the lasagna project. Enzo's senior postdoc there and Federico's PhD student, and they are visiting us for the collaboration within this project, so we profit this opportunity to know a little bit more detail what they are doing. So Enzo will talk about the characterization and modeling correlations in multiplex networks, and at the end we will have a short presentation by Federico on various random blocks of multiplex networks. And they are here until Thursday afternoon, so if anyone is interested in talking with them in a particular thing, just come.
Just to go to lunch together.
Okay.
Okay, thanks Maxi for the introduction. And okay, this is the title of the talk. I will basically give you a brief introduction about what are all these multiplex networks about, because there is it seems like a new buzzword, and I'll try to convince you that indeed it might be not just a buzzword, but that there might be something really interesting in considering the multi-level organization of a complex system in terms of multiplex networks. So, okay. This is a very old thing. It has already been known since the 60s that social interactions are intrinsically multi-level, because each of us is not interacting in the same way with family or friends or colleagues or people to whom you go to the pub together, or so you have several different channels of collaboration, several different meanings in the relationship that you establish with a peer. But this is also true for other kinds of complex systems like cities, in which you can have different means of transportation, and they are actually interacting in a very interesting way. In a city like London, for instance, there's been a very an extensive strike of the tube just last week. And basically, all London transport system was paralyzed for 3 days. So a disruption in one of the transportation layers could be massively disruptive for the other transportation means as well. So considering the multi-level organization of complex system is not that wrong or that ill thought. So the multiplex metaphor basically consists in considering each level of interaction among the units of your system and representing them as different layers of a multi-layer graph, in which basically nodes are identified. So node 3 is the same node, represents the same unit at all the layers, but each layer can have a different topology, so you can interact with different layers with different neighbors, possibly with different intensities. But this is not just true for the social systems, it could also be true for transportation systems, for any kind of network that could be thought as a multi-level network. So what does the multiplex model differs from single-layer classical complex networks? In the fact that indeed you have m replicas of each node, and each node can have different, as I say, different roles on different layers. From a local perspective, these different roles are represented by having a different degree on each layer. But you know that the degree and the degree sequence of a network just is implicitly setting also some other properties of the network, like the distances and betweenness and so on. So this is a short and first approximation for representing the properties of the node, but basically each node property in this framework becomes a vector. So a node is not just represented by a number with respect to degree, betweenness, or centrality, but its features become a network. So I will give you now some examples of new multiplex systems, which are indeed not new at all. Those are all very old and very well-known systems that have been studied as single-layer networks, but indeed are and can be thought as multi-layer and multiplex systems. The first is the authorship network. For instance, APS, the American Physical Science collaboration in American Physical Science Journal. And in a single layer framework, you have the nodes are authors and edges are co-authorship. So you have connected if you have author of the paper together. But as soon as we consider which kind of paper you have co-authored together, then we can have different layers of interactions. Because obviously, if you work in statistical physics, then the large majority of your papers will have first class, which is in the class 6 or in the class 4. You know the class code organization. While if you work in relativity, you will have the class that start with 0. And obviously, the communities that you have or the structure that you have of networks are different, subfields can be different. There are some people whose research is inherently interdisciplinary, and they can have some different they can have published different papers on different layers. Another example is the CoStar network, IMDb. You know, this is a very well-known network in which you connect two actors if they have starred in the same movie. And originally it was considered as a single-layer network, but if you take into account genres, so drama, western, adult movies, then you understand that the kind of interaction could be different. Because some actors are specialized in a genre, but some other actors have played different roles in different genres. And usually if you are a porn star, as we'll say later, there is a little chance that you will ever act in a fantasy movie. And this is something that we will say later. But also, neural networks can be multi-layer. For instance, the C. elegans neural network has been always seen as a single-layer network, where nodes are neurons and edges are communication channels, without making ever a difference between the different kinds of communication, except for very recent papers that have addressed this point. But in reality, we have at least 2, maybe 3 or 4 different kinds of communication channels. So neurons can communicate by synapses that are chemical signals, or can communicate by gap junction that are physical connections between the 2 cells, so channels in which ions can pass by diffusion. And these have different dynamics in terms of spatial and temporal dynamics, so different meanings. And finally, protein interaction. Traditionally, the 2 way of looking at protein or genes interaction has been just either protein-protein association or gene-gene interaction in terms of suppression or activation. But we can put all this information together in multiplex and see what are the relationship and the correlations between 2 proteins being regulated one by the other, or having an association link. And finally, the I-port network, in which nodes are I-ports, and an edge exists if you have a route between these I-ports. In the multiplex version, and due to the availability of new data set, basically what you can do is that you can have a different layer for each I line. So imagine that all the routes operated by one I line represent a different kind of interaction. This is reasonable if you think about it, because all these routes have something in common, which is the strategy of the I line in terms of which airport they have to cover, or which price policies they want to implement, and so on and so on. This is just a very brief summary of the networks we have been analyzing in a recent work about correlations in multi-layer graphs. And you see that we can have, if n is the number of nodes and m is the number of layers, we can have networks from the tiniest one, which is the C elegans with just 300 nodes and 2 layers, to the largest one, which is IMDb with more than 2 million nodes and 28 layers. Even if we can have up to 213 layers in the case of the air transport network of Asia. So the first part is that complex interconnected systems might have, indeed, a multi-level structure, and we shouldn't look, just to new systems. We should also reconsider the complex network that we have studied in the last 15 years, and see if there any new information or new trait that could be considered complex. So the question now is, okay, there could be multiplex. So does multiplexity adds new complexity or just additional complications? Because by considering a certain number of layers for each network, we are obviously adding some complications in terms of representation, visualization, analysis, and so on. So is there any genuinely multiplex new complexity in this structure, or is it just a theoretical exercise for physicists? And okay, so we tackled the problem from different perspectives. Historically, the organization of the talk is backward in time. So the analysis of multiplex correlations came after the first generative models, which is awkward, but sometimes science doesn't have a linear path enough. So we'll first talk about the definition of multiplex correlation. So what kind of correlation can we measure in these about the biogrid data set, which is probably nodes by their degree on each layer, positions in both layers. So if multiplexed wouldn't mean that much, if a position in the second layer as well, because its role shouldn't be that different. Scale linearly with that, more or less. Okay, scaling more or less like 300 nodes, you have just 300 position in both layers. Connected node in another, or could be an average. So whatever you infer by looking at the aggregated network could be wrong, because some nodes could be the role of some nodes could be overestimated or underestimated in terms of. So we started from scratch, starting from the node degree. A binary string which simply says, okay, this node has degree larger than 0 in this. The corresponding degree on layer of node I is greater or equal to 1. Sorry. How many layer is a node active in?
Could you refer here to a T?
I suspect that I say that the node is active if it has at least one link in that layer. It could participate in dynamics in that layer. If it doesn't have an edge, it wouldn't be involved in dynamics. So, and these are the plots of node activity vectors. So, look at each possible value of node activity, and in all the airports and clear, all these distributions are quite broad, which means that there is no typical scale or no typical number of layers in which a node can be involved. Could be 1, 2, 10, 1,000.
So left is airlines.
Left is airlines, and here is APS and INTB. You see, there is a very.
But the nodes are airports.
These are airports, yes. Well, it's kind of straightforward for airports. You can imagine that not all airports have the same importance in terms of number of airlines that they serve. I mean, it's trivial as well for IMDb or APS, because not all airports have acted in any genre, but there are some of them.
Is the sum of the
No, this is just the problem of the when you make exponential binning, you have bin. Right, but it's just because the bin ends at 2.4. And there is the zip distribution of activity vectors. So we rank them by popularity, if you want, and we look how many times that particular activity vector, which is the particular path. And also here you have a pattern. So you could have either a certain probability which is not zero. You can have a configuration of layers. So there is some.
So the maximum B for around
the maximum B for black. No, this means that the same for 1,000 others. This is the is present or not.
Well, but then
No, this is a rank. It's just a rank. And here you have this means that this happens just once, and this happens 10. So to the 10 possible. This is the distribution of PI that we saw before. How many times I find that particular vector in our system, right? You have some kind of recursion. But the same thing could be done not vertically but horizontally. So looking at the activity of nodes on each layer and comparing the activity of layers. So indicating vector which is 1 if a node is active there and is 0. Complex. That are active on that layer. Just that are active on each layer. You see that in show that multiplexity has a role. Number of active nodes, which means there are some islands which serve up to 1/3 of airports in a continent. Right? This is kind of straightforward to understand, but still, there is heterogeneity there. So if you put so what else could you measure in this case? You could measure the first is the times that is happened that given two layers do they have in common over the are these strings. So is active here, then it's not active. This is another kind of correlation. Normalization. Imagine that if there were not any correlation, then you would complexity. But indeed, this is not the case. So you have a quite broad-tailed in general for the case of the airports. That you can have layers that are very similar, so I have layers that are very different, so they have in which you have competition among islands. So of PA, because wouldn't mean again if you flop them, you lose much. For the you have a distribution that is not trivial at all. We actually define a couple of models, or null models, to see the same number of nodes on each layer, and this is not the case. Layer growth, but this is not the.
Excuse me.
Multiplexity is exactly your. That's why I don't understand. No, sorry. What is the percentage of? It's kind of a dual measure of that one. Distance, the more different the two layers. And you see that there is like of an use different in the paper. So far, it's heterogeneously distributed, and they can exhibit have shown that this can assign activity in a random. The real distribution of activity vectors. So if you just shuffle the vectors, then you don't get the same behavior. A third thing is that you could look at, well, in a standard single layer class, we look at Our problem is for a node that has degree k to be connected. Look at the interlayer degree distribution. So how often it is degree k beta on layer beta. These are conjugate and we do the same thing that we did for interlayer correlation. The expected degree of layer beta of a node. Okay, in some cases, like in C elegans in biogrid, we find very not exactly scale-free on all the cases, but it tends to be positively correlated. Three cases that are matter 1, which is statistical physics, and all these parts are interdisciplinary science. Happens for astronomy in general, but there is classical physics. Classical physics is correlated with the degree of classical physics more. Let's go to the movie. Very done a lot of films in drama that has acted also in a Western film. If you think about movies of the 60s, for instance, or people like that, they have. There is a kind of no correlation between also the possibility of having movies and Western, for instance. Completely. So you consider how or it's just enough in adult movies, but it's not can have actually non-trivial interlayer correlation. Generative models to reproduce this kind of interlayer correlations. But this is not true because this model, when it just becomes, we realize that we have it. So, just to remind you, the most criticized models in complex network layer case, it works like new number. And then the probability of degree. And in this case, you get that the square root of time, and this means in the long t limit. What's the multiplex stubs on each layer? This is what we propose. Network on each layer, which can have degrees at different layers. So this say to attach on layer alpha to a certain degree, which is the layer. So you decide to become a friend of somebody, not just work connection, collaborations.
Constant.
Fluctuating values of n doesn't change anything. Of null with a certain average. Change the qualitative behavior. Replicas of the same node could potentially. So a replica can arrive at time t1. Now become connected with somebody on all layers. Like and doesn't work like that in reality. We use two possibilities, so a linear function or a semi-linear function. Two-layer network, this can be generalized to any number. For a node that has degree k and to another. It's the simplest thing you can imagine. It depends on the degree on some layer, but doesn't depend on the degree on the. And for what regards the arrival, which our node arrived first, and then the arrival. The delay is distributed with the power node, the tunable. In a particular range. Layers. And in the case of semi-linear attachment, in the asynchronous arrival, we get scale free with some specificity. And unfortunately, in all models, we can represent this kind of model C elegans by with okay, but for multiplex extension it can catch this simple some other cases it doesn't work. So dealing with multiple
Good enough terms in the diagonal, and you should get
the correlation now introduced by age. So now that it's old, we get a higher degree. And if it arrived at the same time in both layers, the effect of age on both layers will be the same. So you observe positive correlations again. This was my initial intuition, but it doesn't work like that. So just age is introducing, the time of arrival is introducing a lot of positive correlations. So we move to a nonlinear preferential attachment model. I will present the formulas for two layers. Is proportional to call ki the degree of node I at layer 1. Attachment function is symmetric with respect to the parameters. for the attachment same layer and a certain nonlinear function of the degrees on the attachment on the other layer. The other layer on the attachment. And alpha and beta can be real. So what's interesting is that if alpha and beta are both positive or negative, otherwise if they are if connected in one layer but poorly connected in the other layer, and vice versa. With pole stars but not with western alpha. Repeating the same example, but this is the and interestingly, the function of alpha and beta, and basically this is the inverse participation ratio. I have homogeneous degree distributions. There is one node in each layer that attracts an extensive fraction of all the edges. Extensive means that it goes with n as the number of nodes. These regions here we have power laws. So we can have all kinds of combinations of power law and homogeneous and condensed degree distributions. But what's interesting is that we can have both positive degree of beta just in the value. And for the beta is here. So basically with this model an additional parameter. Beta equals 0, alpha equals 1. Is beta equals 0 and we tried to solve the model by the infinite process. The standard way of solving a growth model. I'm almost done. So you imagine that the degree of a node is equal to the expected degree that it will have on all the possible ensemble of realizations, and you call kappa I the degree of node of layer 1 and phi I the degree on layer 2. And if you write the in-field equations in terms of rate of differential equation on Ki, then you get an equation for the degree distribution which works quite well in reproducing the non-condensed phase. This is in general a Weibull distribution and becomes a power law just at the edge of the condensed phase. But the bad news is that this predicts, the mean-field approach predicts always positive interlayer degree correlations, meaning that the average degree of a node on layer 1 will always be the same of the average degree on layer 2. This is obviously false.
Why in the equation the denominator is so trivial, it's linear with t, because that should be the total.
Because you have another number of edges with this concept.
But the numerator goes degree to some exponent, right?
Yes, but this has to be determined self-consistently for t that goes to infinity.
No, because that, I mean, if you have degree to an alpha, the addition of that is not linear with t.
Yes, but the problem is that C has alpha and beta, k to the alpha and phi to the beta inside. So C is not.
I should have also.
Yes, but you make the assumption that this is constant if t is large enough. which is actually true. So this is valid in the long time limit. So we revert to the other possibility that you have, master equation approach. If you write the master equation approach, you recover the functional form of the degree distributions, the boundary of the condensed phase in a very good way, and we can get both positive and negative inter-degree correlation. So the master equation is the only way we have, in this case, to understand something about the model. So the fifth fact is that analytical models, analytical tools that are valid for single layer networks, like the mean field approximation, would not work in the case of multi-layer systems. So take home message. I think that multi-layer networks represent a new perspective in complex networks. I'm trying to use this postdoc fellowship to show that indeed multiplexity is new complexity. It's not just added complications. We already have some hints, because there are non-trivial correlation patterns which are irreducible to single layer graphs, but there are some other hints about dynamical features of multiplex networks that are not reproducible by single layer graphs. And they will need, the analysis of multi-layer graphs will need new tools and possibly new analytical methods. So it's interesting it's an interesting field to invest energies into. These are some references I think that might always over.
Vincenzo, should we take questions now before moving to Federico?
As you prefer.
Probably. Okay. Questions?
I have one comment.
Yeah.
I agree with you in that these multi-layer networks, offer a perspective, and they will be reproducible. But some of the things you have presented are too abstract for me, and I need to go to one of the examples you have gone. That is the protein interaction networks. So, first question, just to fix it, is how many layers have you?
In this case, in this paper we consider just two layers, genetic and association. But in the same data set, we could recognize up to 7 different layers, because you have different kind of physical association and different kind of genetic interactions, like suppressive or.
So genetic, you mean?
That protein is a transcription factor for another protein. Yes.
And the other one, association?
Association is either physical association, or maybe they have some other kinds of physical interaction, either in terms of densities, or not just in terms of forming a new compound, let's say. I'm not an expert in this. We asked it to a biologist that said, okay, you can't just put all the physical association in one layer because they are diversified. So I'm not an expert on that. We know that I know that we were able to identify up to 7 layers, and so we did in a more recent paper in which we asked ourselves the dual question: how many of these layers should we preserve? How many of them are really significant? Or is that?
So then I have another small question. Do you consider, in some sense, the role of the dynamics, not of the detailed dynamics, but for instance, protein interaction networks many times have exhibit very different time scales, for instance. So there are developmental interactions that are very slow, others that are faster.
Well, this is something that we should sooner or later take into account, because multiplexity is not just a matter of different roles, but it's always a matter of different spatial and temporal scales. So it may be that this diversification in multilayer doesn't make any sense if one process is much faster than the other. So in that case, you should just consider the slowest one, which is driving the dynamics in a certain direction. So this is obviously an ingredient that you should put in your modeling. But we are just at the beginning. I mean, the first paper on multiplex networks is less than 16 months ago. So,
And response okay.
we have time to discuss, by the way. I'm here until
How do you measure correlations? I mean, they are just 2-point correlations, let's say?
Okay, at this point, I mean, this preliminary work, we have worked either with correlation functions, that is the average degree, it's a standard way in single layer networks, or you could use the different kinds of correlation coefficients, linear correlation coefficients, or rank correlation coefficients. But we know that we need a more accurate way of measuring correlations, and in this last non-linear growth paper, we suggested also to look at mixed correlations. So, how often does it happen that a neighbor of a hub on one layer is a highly connected node on the other layer, and vice versa?
Because you know that there are functional
second part.
Okay.
Yes, second question. In many examples, it's quite clear to define a priori what are the layers. So in the transportation level, you have air transportation, gas, but in other cases, it's quite difficult. I just focusing on the case of the authorship. Then this PAX classification of the fields of physics is really arbitrary. In fact, APS has among it. In many, there is a line of work of trying to identify the subjects, the topics in science by community detection. So this will be a community. In that case, the layers will be the communities. Have you thought in this? I mean, in this case, there will be some positive correlation, so some meta definition of communities, such as having a strong positive correlation. This will be one community. Having a strong negative correlation between layers means that the layers are different communities. Have you thought in this relationship between communities?
There is an interesting duality between communities and layers. At least in some cases, like the authorship network, in which you really think that a field is just defined by the community of authors that belong to that field. I perfectly agree with this. And it's not a matter of PAX. It's a matter of what your research is about. So it's much more much better identified by that. But in general, I'm not that interested in saying, okay, this PAX classification is a good way of showing that this network is a multiplex. You could choose any other trait that you want to diversify the layers. My message here is that whatever is the trait you're interested in, if there is a trait that could be considered as discriminant to put edges in different layers, then you should probably give it a try and try to understand if this diversification makes sense. So, I mean, I don't want to enter in the problem of probably identifying layers. The message is more fundamental. If you have a way of distinguishing two different edges for a feature, then you should probably give it a try, because by distinguishing them, you would find unexpected correlations, especially if they have different meanings. So this is, we can discuss it.
Yeah, there is time for discussion next day, but I think now we should move to the short presentation by Federico.
All right, the right one. That one, yes. Try now. Try now. Why isn't it work?
You see this laser?
No,
It's another program.
Okay, you can use it.
And the people are the old style pointer.
Don't worry, I think.
Just go ahead.
All right, okay. Okay, so in this presentation I'm going to talk about bias random walks and multiplex networks, which is joint work again with the ENSO and the Vita Laboratory University of Milan. So I'm going to start by introducing what bias random walks are, and provide a set of analytical results that we obtain for the stationary distribution and the entropy rate of such processes. And in the end, I will play a little bit with the possibilities given us by reaching complex topologies of multi-layer networks with respect to the bias function. So I will define different classes of bias random walks, and this is only possible for multi-layer graphs. Random walks have been studied extensively also in the field of complex networks, since they represent the basic model to understand diffusion, and have also applied we've also been applied successfully in a variety of different topics, from characterizing centrality to detect communities and so on. For such processes, walkers are strolling around the graph, and at each time step, each walker jumps from one node to one of its neighbors, selecting the neighbor at random. The idea of bias random walk is to modify this probability by making it proportional to a function of some topological property of the destination node. So the bias function is this f in orange here, which is a tunable function of the destination node, and in this way we can systematically prefer or prevent moving towards nodes with given characteristics. And a very interesting case is the one of degree bias random walks, where the bias function is a function of the degree of the destination node powered to a bias exponent b. So in single layer networks, if b is smaller than 0, we are actually biasing the walks toward nodes with low degree. Conversely, if b is greater than 0, we are biasing the walks towards the hubs of our system. What happens in multiplex networks is that the basic units of the system may be connected by a variety of different relationships, and the links of different natures are embedded in different layers, and each layer is described by a different adjacency matrix. In general, in such systems, information but also epidemics or rumors may spread across these multiple yet interacting channels, and the generalized transition matrix takes the following shape for bias random walks, where Oij are the entries of the so-called overlapping network, which is given by the superposition of the different adjacency matrices, the different layers. And what is F now? Well, F can be either a combination of single layer properties, like the degree at all layers, or could also be a function of some synthetic multiplex properties. And I will talk in more details about this later. But for now, we just discard the analytical expression of the bias function, because we have a set of analytical results which do not depend on the explicit form of F. So, we are looking at this dynamical process, and of course we are interested in the stationary distribution of such process, that we know it exists if the overlapping network is primitive, has at least another side. The nice thing is that we can always solve for this stationary distribution, and that this expression does not depend on the functional form of f. How do we compute the stationary distribution analytically? Well, we first compute the probability to move from node I to node j in exactly these steps, and this is given by this product of transition matrices, and we are summing here all possible intermediate steps. We also consider the reciprocal term, so the probability to go from node j to node I in exactly these steps. And the nice thing is that for undirected layers, this very simple condition holds, so this is the only hypothesis we have to state. And actually, in the limit of long times, this directly gives us the solution for the stationary distribution, that, as you can see, does not depend on the specific form of f. And we can also compute the stationary distribution not for the node I, but for classes of nodes with a given degree. And I won't go into the details of the derivation, but this expression is linear with the bias function, again independently from the exact analytical expression of the bias function, and is also linear on the total number of communication channels for that node. And another nice measure for dynamical processes on graphs is the one of entropy rate, which accounts for the mixing of the trajectory of the walkers over such graph. And it depends both on the topology of the graph, but also, of course, on the dynamical features of the process. And is defined in this way, and And again, we have a closed expression for h, so we don't have to run the simulation to compute h, but it is sufficient to know the topology of the graph, and of course the motion rule we are using, which is here included in the bias function. And the idea is that h gives us a measure of the dispersiveness of the walkers, and the dispersiveness is 0 when there is only a trajectory which is allowed, and this is the lower bound for h, which is equal to 0, and only one trajectory is allowed. What happens when h can be maximal? When all the trajectory that have the same length have the same probability. And we were able to show, in analogy with the single layer case, that h max, the maximal entropy rate, is equal to the natural logarithm of the highest eigenvalue of the overlapping matrix for multiplex networks. So, as Enzo was saying in the previous talk, we saw that the multiplex degree is actually a vector. So the very basic idea for a bias function would be the one to consider a combination, either additive or multiplicative, of single layer properties at all layers. For instance, the degree power to a bias exponent. Of course, this bias is very accurate because it allows us to disentangle the effect in the dynamics of the different layers, but it is computationally expensive since its computational complexity scales up linearly with the number of layers of the system. So our question was, is it possible to produce an accurate bias in a better computational way? And in a previous work, which was about structural measure for multiplex networks, we noticed that in general, single layer properties may have very different patterns of different layers. In this case, we had data about a group of Indonesian terrorists that trust each other or not, but also can have common operations with common communication. And as you can see, the pattern for the degree are very different. This is the aggregate layers, and these other three are all the different layers. The idea was to provide a good synthetic but still effective sketch of what was going on. In order to do so, we introduced these two multiplex coordinates in the space of the degree. The first coordinates, that we call the overlapping degree, is simply the total number of connections of each node, discarding nature. And then we can rescale it by means of the z-score. And the other coordinate is the so-called multiplex participation coefficient, which accounts for the homogeneity of the distribution of the connection across the different layers, and is equal to 1 when a node is a truly multiplex node, so it has connection of among the same numbers in all layers, and goes to 0 when a node is actually focused. In this way, we are able to perform this cartography of the system, where we have simple nodes and hubs, but we can also have focused, mixed, and multiplex nodes on these other axes. And as you can see, fix the total number of connections, there is still a strong heterogeneity in the distribution of such connection. And for instance, nodes 16 and 34 that have exactly the same number of connections are very different, play very different roles in the system, because node 16 is a truly multiplex node, while node 34 is actually focused on the operational layer. And of course, the two nodes that play very different roles, for instance, with respect to vulnerability or centrality in the system. So the idea is that we can perform what we call intensive bias random walks by writing f as a function of these two parameters. And what I want to show you is that using different motion rules significantly affect the stationary distribution. For instance, the multiplicative rule broadened a lot the stationary distribution, and since Enzo was talking about interlayer correlation, we can have similar effect by tuning the correlation coefficient broad. So if the layers are very correlated, the distribution is broad. Otherwise, if the layers are very anti-correlated, the distribution is way less broad. And this is the theoretical value for the maximum of the entropy rate as a function of the correlation coefficient broad. So this is an increasing function of the interlayer degree correlation. But this is just the theoretical value. What happens if we perform our bias random walks, for instance, with an additive rule or a multiplicative rule for a two-layer network? And as you can see, the phase diagram, in this case of the entropy rate, is severely affected by which motion rule we are using. And the nice thing, however, is that a very good approximation of the theoretical maximum value is obtained in both cases, here and here. Since in both cases this theoretical maximum value is obtained for positive values of the bias exponent, this allows us to assess the importance of multi-hubs, nodes that are hubs at all layers, to obtain the maximal dispersiveness of the system. And here I want to show you also that interlayer correlation again play an important role also in the phase diagram of intensive bias random walks. And while we have a line of maximum values here for the entropy rate in negatively correlated layers, which means that whatever values of the exponent for the participation coefficient, we can always choose, we can always tuning appropriately the bias exponent of the overlapping degree to obtain maximal dispersiveness. This feature is lost for correlated layers. So to sum up, we generalize the bias random walks to the case of multi-layer system, and I showed you some results, some analytical results which do not depend on the bias function with respect to the stationary distribution and the entropy rate of the process. We played a little bit with the possibilities given us by the richness of the structure of multigraph with respect to the bias function. We defined two new classes of bias random walks, which are the extensive ones and the intensive ones. And in the end, we assessed the importance of the different motion rules, but also interlayer degree correlation on either the stationary distribution and the entropy rate of the processes. And this work will appear soon on the archive, while previous work on the multiplex degree and multiplex participation coefficient, but in general also about other structural measures for multiplex networks, such as multi-layer clustering on configuration of interdependent shortcut path, appeared earlier this year on Physical Review. Okay, thank you.
Thank you, Federico. Any question or comment on this part? No? Good. So we can finish there. We can finish here, and as I said, both Vincenzo and Federico will be here until Thursday afternoon for 2 months. Welcome to discuss.